Why can't you trust atoms? Well, you do need to know about them for your GCSEs. Let's have a look at the basics first. This is the atomic model we know, where we can work out the number of protons and neutrons and electrons in it. So just having a look here, the ones in purple, there are 3 protons. The neutrons in pink, there are 4. So what that means is for this element, which happens to be lithium, we can write the atomic number as 3 and the mass number as 7, because that is all the different particles in the nucleus, which is protons plus neutrons added together. So the mass number is always the bigger one. Make sure you don't get that mixed up. As well as that, we also have electrons orbiting in red in my diagram around the edge of the atom. Now here there are 3. There have to be 3 because it is an atom. Atoms do not have a charge. They are uncharged or neutral. So what that means is that the number of positive protons has to be balanced by the number of negative electrons. So in that case, we would have 3 protons and 3 electrons, meaning the atom has a charge of 0. If it doesn't have a 0 charge, it's not called an atom, it's called an ion. Ion meaning either it's got a positive or a negative charge because it's lost 1 or 2 or 3 or gained 1, 2 or 3 electrons. Now, let's take another example of lithium, which this time has a different mass number. The same proton number, but different mass number. Now, same number of protons means that it has to have a different number of neutrons, and we call that an isotope. So same number of protons as another atom, but the different number of neutrons, meaning either one less or one more. Either way, we call those two things isotopes of the same element. Now, this model I'm showing you here is called the Bohr model, B-O-H-R, which we'll look at a little bit later, but that's the one with the electron shells that you'll be familiar with from chemistry. And in terms of GCSE, it's the most recent atomic model you will find. We're going to look today at what the differences between the models are, but also an experiment that we used in science to work out one of the models didn't have enough evidence for it, so we ditched it for a new model. Now, the 2 models we're going to look at mainly today are these 2 in the top right, which is Plum pudding model, which was replaced in the scientific community by the nuclear model. So the Plum pudding model is named after a popular pudding in Victorian times, which we don't eat anymore, but it's kind of like a blueberry muffin. It's like a kind of stodge of cake or muffin with these tiny little particles dotted throughout it. Now these are negative electrons. Now I've drawn 4 here. Realistically, there are lots, so you can't really draw them on, but there's lots of them all embedded in this ball of positive charge. So they balance out to make it neutral. Now, gentleman called Ernest Rutherford in around about 1909 devised an experiment to test whether this was the correct model of the atom or not. So we're going to look at his experiment, the setup, and what conclusions he drew. Now, first of all, what he expected to happen if the Plum pudding model was true was that the alpha particles, when he fired them at a atom or anything, if the Plum pudding model was true, then the alpha particles would fly straight through. They wouldn't be deflected because there's only very, very small negative charges in amongst the positive charges. What he actually found was slightly different. So he's fired these alpha particles, which are positively charged particles, at a thin sheet of gold foil. Now, this gold foil was chosen because it was really malleable, but also a very heavy metal, i.e. lots of protons in the nucleus. So it's done in a vacuum, so the alpha particles wouldn't collide with any air particles, and there was a detector all the way around it. Now, what he found out was that instead of going all the way through, some of them bounced back at different angles. So let's have a look at why this might have happened. If we look at the zoomed in on the nucleus of the atoms, which was turned out to be what the atoms were like, as the alpha particles went close, those that were close enough to the nucleus were deflected by a force from the nucleus. Now, that force was responsible for the atoms changing direction. Now, in an exam question, this could be a 6 marker, it could be 3 marker. Comes up a lot. We need to know Rutherford's observations, but also his conclusions. So what did he observe and what did he figure out from that? Now, it's really important when you're answering these questions, it is not proof. These are all evidences. Like in the scientific community, we do observations from experiments, and you have to mention that word. So observation 1 was that most of the alpha particles went straight through the gold. Observation 2 was that some of the alpha particles deflected back, or deflected at an angle, we can say. So scattered kind of all over the shop, really. third observation is that very few, and we're talking about 1 in about 10,000 alpha particles, deflected through very large angles, so back at high or large angles. We're talking about this one here that kind of bounces almost directly backwards. Now note I've said deflected there, not reflected. So the conclusions you can make from these observations, the fact most of them went straight through, is that most of the atom is empty space. There is nothing there. The fact that some of the alpha particles were deflected shows that there is a positive or a small positive charge in the center, or positively charged nucleus. And part 3 was related to the size. The nucleus must be very small. The fact that not many were deflected. We're talking about 10 to the power minus 10 meters here. Very, very, very small nucleus, which was completely different to what they thought at the time. So please say deflected, not reflected, is a different thing. So let's talk about this detail then. I mentioned a force earlier. The force is called electrostatic repulsion, or the electrostatic force. It's the same force as when we learnt about static electricity. Two positive charges come together, or two negatives, they repel. The reason is because alpha particles are positive, so is the nucleus. So there's a force exerted from the nucleus onto the alpha particles. Okay, so let's talk about the Bohr model in a little bit more detail. So the electrons that are in those shells, they can move, unlike in chemistry. Now, when they might move would be whether the electrons can absorb or take in some electromagnetic or EM radiation. They move up to the next shell. If they emit electromagnetic radiation, they move down to the shell below. So this is a very specific part of the course here. It's basically A-level physics. It came up in the 2023 paper, so it's definitely worth knowing. Okay, so where are we with the atomic model? So that's the Bohr model. Let's talk about then just the nuclear model. If you're asked to describe that one, we need to be specific on what we are saying. So we've got at the center of the atom, we've got a very small nucleus, and we've got electrons orbiting. Now note they are not in shells. The nuclear model did not prove shells. That was the Bohr model a bit later. So small positive nucleus, and we've got most of the mass is concentrated there. So as well as talking about charge, you should be able to talk about mass and where that would be at the different points of the atom. And the electrons orbit, so not in shells, but just orbit around the atom. Now, one other thing that came up in the 2023 paper is worth noting is the order at which things were discovered. So electrons we knew about since the mid-1800s with electricity. Then Rutherford discovered the nucleus. Then after that, the individual protons were discovered. And the last thing of all was the neutrons, because they are neutral, very, very difficult to discover.